In the name of Almighty God, I'm Mahsa Hassan Kasha, and today I want to talk about heat transfer by free convection. Heat transfer by free convection, also called natural convection, is a process where a fluid moves and transfers heat due to density differences caused by temperature variations without an external force like a fan or pump. Warmer, less dense fluid rises while cooler, denser fluid sinks, creating a natural circulation loop that carries heat. This process is responsible for phenomena like atmospheric and oceanic currents, a hot drink cooling, and the circulation of air in a room. And how free convection works. The first one is density gradients. When a fluid is heated, its molecules spread out, causing it to become less dense. Conversely, a cooler fluid becomes denser. And the buoyancy force, gravity acts on these density differences, creating a buoyant force that pushes the less dense, warmer fluid upward and pulls the denser and the cooler fluid downward. The next one is circulation. This upward and downward movement of fluid creates a natural circulatory flow which transfers heat from the hot object to the cooler parts of the fluid. And examples of free convection: a hot drink cooling. The air just above the hot coffee becomes heated, becomes less dense, and rises while cooler air sinks to replace it. The next one is heating a room. A radiator heat that air around it. This warm air rises to the ceiling and cooler air from the floor is drawn in to be heated, creating a continuous circulation pattern. And the next one is atmospheric and oceanic movements. Free convection is a major driver of large-scale fluid motion in the atmosphere and oceans. And the next one is land and sea breezes. This is a classic example of natural convection where differential heating of land and water creates a cycle of air movement. The next one is cooling electronics. In some electronic devices, free convection is used to dissipate heat through forces. Force convection is more common for high power devices. And free convection or natural convection is a spontaneous flow arising from non-homogeneous fields of volumetric and mass forces, gravitational, centrifugal, Coriolis, and electromagnetic, and etc. If density variation delta rho is caused by a spatial and non-uniformity of temperature field, then a flow arising in the Earth's gravitational field is called thermal gravitation convection. The density variability may also result from a non-uniform distribution of concentration of any component in a mixture or from chemical reactions difference in phase densities or from surface tension forces at the phase interface. In this case, concentration diffusion or convection is implied. Free convective flows may be laminar and turbulent. A flow past a solid surface, the temperature of which is higher or lower than that of a surrounding flowing medium, is the most widespread type of free convection. And here in this simulation, schematically illustrate characteristics examples of free convection. At the beginning of heating of a vertical surface, x is equal to 0, a laminar boundary layer is formed. The layer thickness grows along the flow direction and at a certain distance corresponding to xc1, the fluid flow becomes unstable, changing within the range from xc1 to xc2, from laminar to turbulent. To this character of fluid structure variation, there corresponds the change in the coefficient of heat transfer Ix, which in the case of the developed turbulent Fc remains constant along the plate length, where the characteristics of thermal turbulence become statistically equal. The pictures of Fc development in the flue past a hot sphere or horizontal cylinder are qualitatively similar. On bodies of large diameters, a turbulent boundary layer develops, thus forming an ascending turbulent thermal plumb in a trailing edge. From hot bodies of small diameters, a laminar thermal plumb ascends, which at some distance from a body becomes turbulent. In a narrow and closed cavities, Fc flow is much more complex due to the interaction between near-wall fluid flows formed on the heat exchange surfaces. On heating one vertical wall temperature Th and cooling the other temperature Tc1, the modes with a common fluid flow are possible through the entire cavity that involve local secondary flows near vertical walls as is exemplified in here in this simulation by Fc in a square cavity. A flue in a narrow slot between parallel vertical plates is formed in the form of periodic circulations. In a horizontal fluid layers between cooled upper and hot lower walls, the fluid flow has a cellular form with hexagonal cells. In the center of which fluid ascends from the hot surface to the cold one, whereas in the periphery it descends. Such a form of the fluid flow was first observed in Bernard in 1901. With increasing heat flux, the cells are destroyed and the flue converts to a turbulent one. In the theoretical analysis of Fc flues and heat transfer, the laws of m- momentum, mass, and energy conservation at certain boundary conditions are used. The Buoyancy approximation of weak thermal convection is widely applied. For example, density deviations from a mean value are considered to be negligible in all the equations, except for the equation of motion where they are taken into account in the buoyancy force term. For small temperature drops in a flue, the relation Pt or ρt may be considered a linear, where ρ0 is the fluid density at temperature T0, and beta is equal to minus a differentiation of ρ divided by differentiation of 2 of T and P divided by P is the volumetric coefficient of thermal expansion. Numerical values of B are usually small, and therefore the density variation is taken into account only in those cases where it affects the gravitational forces. And this approximation correlates the coefficient of volumetric expansion of a medium B with the gravity acceleration g, and they enter into the governing equations only as a product. Physical substantiation of this approximation is based on the smallness of acceleration in Fc fluids as compared with the acceleration due to gravity. Comparison with vast experimental material indicates the fact that this approximation well reflects the main specific features of thermal gravitation convection in a wide class of real convective fluids. As is shown by experimental data, in many cases of Fc, the main variations of the characteristics of thermal and hydrodynamic fields are concentrated relatively narrow boundary layers near the heat transfer surface where viscous forces are commensurable with inertial and volumetric forces. The smallness of a boundary layer thickness as compared with characteristic dimensions of bodies allows one to introduce additional simplifications into the equations of motion and heat transfer. The concept of a boundary layer is far more complex for Fc than for forced convection because thermal and hydrodynamic problems cannot be treated separately due to the fact that fluid flow is completely determined by heat transfer. The main motive force, the difference between wall and surrounding temperature, noticeably manifests itself only a thin near wall zone at this region of a temperature field with a thickness of a sigma T is called a thermal boundary layer. The difference of temperature in the boundary layer creates a volumetric buoyancy force which causes motion. At the surface, the fluid is stationary, which is the no slip condition. With distance from a wall, the velocity u gradually grows to a maximum, and then under effect of viscous friction, it vanishes. Beyond the limits of this dynamic boundary layer, there is a region of inviscid potential flow, the distance along the normal from the wall to the place, where the velocity differs from 0 by 1% of the value of U max, is taken as the dynamic boundary layer thickness sigma. And use of nanofluids in solar energy system, natural convection. Natural or free convection is a type of heat transfer in which there is no external force on the fluid to move. It is only due to the density difference originated from the temperature gradient. Depending on the geometry and flow pattern, natural convection is divided into the two categories, internal and external convection. In the inner fluid, the fluid field is surrounded by solid boundaries, while in the outer fluid flows around the solid body. Natural convection is more complex in internal flow issues than external ones. External flow issues can be modeled using the classical boundary layer theory, assuming that the area outside the boundary layer is not affected by solid boundaries. Depending on the type of thermal boundary condition used in internal natural convection problems, there are two categories. The first one is cavities whose sidewall are heated or cooled, in which case the temperature gradient is perpendicular to the direction of gravity acceleration. And the second one is cavities whose layers walls are heated, in which case the temperature gradient is in line with gravity. Free convection happens inside the cavity with heated side walls of the first type, and the Rayleigh-Benard convection happens between two infinite parallel plates of the second type. Natural convection in enclosed enclosures has wide application in industry and engineering. According to the chamber heating model, there are various applications such as cooling of electronic equipment, lubrication system, heat exchangers, solar collectors, electric furnaces, and solar water desalination and melting and freezing processes in engineering. Extensive research has been conducted on the natural heat transfer of nanofields, and in addition, the heat transfer of natural convection in the porous media has attracted the attention of many researchers. The natural convection under magnetic fields has also been the subject of investigations by several researchers. A large eddy simulation of natural convection boundary layer on a vertical cylinder and natural convection is an interesting scientific subject for which many aspects need further research. The application include not only industrial fields like power generators, reactors, turbines, heat exchangers, and other power conversion devices, but also natural phenomena like atmospheric and oceanic currents, bioheat transfer, greenhouse effects, and heat transfer in stellar atmospheres. Compared to the number of experimental and numerical research which have been carried out for the other methods of heat transfer, few belong to to the natural convection field. Among the experimental research, the latest is that reported by Tsuchi and Nagano in 1988. In that work, characteristics of natural convection boundary Y layer are compared with the previous investigations. It is shown that natural convection boundary layer has a unique turbulent structure which is rarely seen in other turbulent boundary layers. The results suggest that for values of y plus between 20 to 100 is not correlated with the mean velocity gradient. However, comparison of Reynolds shear stress with previous experiments showed a different behavior near the wall. Although no negative region was observed by Nagano in 1988. Almost all previous works has shown in negative region close to the wall. It is also shown that the cross-correlation coefficient for shear stress becomes zero near the wall, which is in contradiction to analytical analysis. Turbulent natural convection around a heated vertical slender cylinder was studied by Pearson and Carlson in 1996, and new turbulent structures were presented for the near wall region. Again, it was shown that there exists a negative shear stress region close to the wall, comparing normal stresses and temperature fluctuations with those proposed by Nagano in 1988. Different behavior can be observed between these two experiments. Although the temperature fluctuations presented by Nagano in 1988 are larger than the extreme-wise normal stress. It is vice versa in Pearson and Carlson in 1996 work. However, the location of the peak remains in close agreements. Natural convecting boundary layers have also been studied using DNS or LES. However, most of the studies include fluid, either in cavities or differentially heated channels. Among them are researches conducted by Mickey and his colleague in 1993, and other researchers that happened. From previous investigations, it could be found that natural convection phenomena has still many aspects which are not clear, and there are some other aspects for which there is no consensus. Another fact is that very few research have been conducted on the natural convection boundary layer along a vertical sealant, and most of the studies are performed on flat plates, channels, or horizontal sealants. This fact, besides existence of an experimental apparatus in the mechanical engineering department of Chalmers University of Technology, created the motivation for designing an LES problem in order to study the natural convection heat transfer along a vertical sealant. And what about the natural convection? Natural convection is a form of convection heat transfer in which the driver of the bulk motion or advection is self-induced forces. These forces may be due to temperature or concentration gradients. In this book, we focus our attention on natural convection flow and heat transfer due to temperature gradients in the light of the above statement. It is intuitively apparent that flow and heat transfer will be strongly coupled in natural convection. Because there is bulk motion, natural convection heat transfer will be several times more than what one would obtain in molecular conduction. Even so, because no external agency such as a pump or blower is involved in natural convection, the velocities will be small, typically of the order of centimeter per second or tens of centimeters per second, as opposed to several meter per second, which is typically seen in forced convection. As a consequence of this, natural convection heat transfer rates will be lower than forced convection in a particular situation if all other controlling variables like temperature difference, geometry, and medium are the same. Recall that traditionally, convection aided by an external agency like a pump or fan or blower has come to be known as forced convection. In view of this, natural convection, where there is no forcing by an external agency, so to speak, is also known as free convection. Consider two infinitely wide horizontal parallel plates at temperature T1 and T2 respectively. Let the space between the two plates be occupied by a medium like air. Two possibilities exist in shower here. The next chapter is turbulent natural convection heat transfer in rectangular enclosures using experimental and numerical approaches. Natural convection is one of the most important modes of fluid flow and heat transfer, and this simulation presents a review of the research on turbulent natural convection in rectangular cavities using numerical and experimental techniques. In this review, we have attempted to summarize the published paper on this topic with some interesting and important results. Numerous configurations of the enclosure with different initial and boundary conditions, heat source locations, and radiative properties of medium and walls have been considered under the effect of various parameters such as the Rayleigh and Prandtl numbers, surface emissivity and cavity inclination angle, thermal properties, and etc. Finally, some suggestions have been provided for future studies in the considered area. And what about the convection heat transfer in enclosure with a linear bodies, a review on single and two-phase nanofields model, preliminarily illustration. Natural convection or free convection is a flow that represents the motion of different fluids, including water, air, molten metal, and others. The fluid flow in natural convection problems is induced by natural means such as buoyancy, and buoyancy forces may arise in a fluid with a gradient of density in which body forces are proportional to their density. Since the natural convection induced velocities are relatively low, the heat transfer coefficient encountered in these cases is usually low. Natural convection is an interesting scientific topic for which many aspects need further research. It has attracted a vast deal of attention from researchers and scientists due to its wide applications either in nature, such as natural phenomena like atmospheric and oceanic currents, heat transfer, greenhouse effects, and heat transfer in stellar atmospheres, or in engineering, such as in the design of equipment for electronic cooling, insulation of aircraft cabin, nuclear reactor, and heating and ventilation control of building, and so on. In this review section, we will introduce various studies where the natural convection generated inside enclosures with internal bodies directly or indirectly affecting heat transfer through the enclosure's fluid. Because of its unique and important applications such as microwave heating, electrochemical batteries, solar to thermal energy conversion, geophysics, and nuclear reactors, natural convection heat transfer induced by internal heating or absorption has received and continues to receive much attention. And what about the convection heat transfer in enclosure with inner bodies? A review on single and two-phase nanofield models. Natural convection or free convection is a flow that represents the motion of different fluids, including water, air, molten metal, and others. The fluid flow in natural convection problems is induced by natural means such as buoyancy. Buoyancy forces may arise in a fluid with a gradient of density in which body forces are proportional to the density. Since the natural convection induced velocities are relatively low, the heat transfer coefficient encountered in these cases is usually low. Natural convection is an interesting scientific topic for which many aspects need further research. It has attracted a vast deal of attention from researchers and scientific due to its wide applications either in nature, such as natural phenomena like atmospheric and oceanic currents, heat transfer, greenhouse effects, and heat transfer in stellar atmospheres, or in engineering, such as in the design of equipment for electronic cooling, insulation of aircraft cabin, nuclear reactors, and heating and ventilation control of buildings, and so on. In this review section, we introduce various studies where the natural convection generated inside enclosure with internal bodies directly or indirectly affecting heat transfer through the enclosure fluid. because of its unique and important applications such as microwave heating, electrochemical batteries, solar to thermal energy conversion, geophysics, and nuclear reactors. Natural convection heat transfer induced by internal heating or absorption has received and continues to receive much attention. And what about the convection heat transfer enclosure with inner bodies? A review on single and two-phase nanofluid models. Natural convection with the internal bodies, regular fluid or NCIBRF. Preliminary illustration. Natural convection or free convection is a fluid that represents the motion of different fluids including water, air, molten metal, and others. The fluid flow in natural convection problems is induced by natural means such as buoyancy, and buoyancy forces may arise in a fluid with a gradient of density in which body forces are proportional to the density. Since the natural convection induced velocities are relatively low, the heat transfer coefficient encountered in these cases is usually low. Natural convection is an interesting scientific topic for which many aspects need further research. It has attracted a vast deal of attention from researchers and scientific due to its wide applications either in nature, such as natural phenomena like atmospheric and oceanic currents, bioheat transfer, greenhouse effects, and heat transfer. And here you can see that in the capsule simulation, the material is water and liquid, and we have used two different physical modules, laminar flow and heat transfer in fluids. And you can see the temperature here, its velocity, pressure, and temperature and fluid. Thank you so much for watching my tutorial video until the end, and also you can download this video and the code related to this video from github.com/masterscript, and the name of this simulation is free convection mph.